All right, you're almost done with this learning activity, but before we part ways, I want to take a moment and think about how selection can manifest itself. And so we're going to stick here with mouse color phenotypes because it's something that we're definitely familiar with after our rock pocket mice. So this is your ancestral population of mice. There are 5 phenotypes for coat color ranging from white to tan to dark. And we see a normal bell shaped frequency distribution where this is your most common phenotype, followed by these. And these are the rare phenotypes out here on the tails. Okay, so recall the Valley of Fire in your rock pocket mouse activity. So we had these dark lava substrates, right? And there was selection against the lighter phenotypes. So that would be represented down here on the bottom left. These phenotypes were weeded out, right? And the distribution of phenotypes shifted, in this case to the right, towards those darker morphs. This is what we call directional selection. Of course, directional selection can go either way. You could imagine in the Arctic where there would be selection against darker phenotypes, and the distribution may shift to the left instead of the right, all of that driven by predation and, of course, differential rates of survival. Okay, so now I want you to imagine a beach. Maybe it's in the Hawaiian Islands on the Big Island, and there's light colored sand surrounding dark pockets of volcanic rock. Okay, an environment like this might drive what's known as disruptive selection. So this particular light colored phenotype is doing well on those patches of sand, and this particular dark phenotype is doing well on the lava rock. But the most common phenotype doesn't blend in well to either one of those environments, so it is being selected against. So in this case, the new distribution is now bimodal, right? We have 2 peaks, and the most common phenotypes are selected against. This is known as disruptive selection. All right, and then finally we have stabilizing selection. This is just when a particular phenotype, in this case, it's the mode, the most common phenotype, it offers such a powerful selective advantage that the alleles for the other phenotypes, those are just completely wiped out. They're selected against. So taken to the extreme, stabilizing selection can actually fix the phenotype, where 100% of the individuals express it and all the other alleles are lost. So, in conclusion, natural selection is clearly an obvious and major driver of evolutionary change.